Hi everyone, we are going to talk about unsupervised learning today, starting with principal component analysis, and we have a total of 2 lectures on principal component analysis. This is part 1. So what is unsupervised learning? So far in the machine learning courses, we've been focusing primarily on supervised learning, which is a form of machine learning where both X features and Y feature or outcome are available. The Y response values are very important because they provide the correct answers or labels that we need to verify what is the truth. So we usually call Y the ground truth. Okay, but however, not every data set comes with the Y outcome variable. Sometimes you don't know what the correct answer is. There's no label for your data set. You only have X features available. When you don't have the Y variable or the correct answers or the labels, then we really don't have a way to check your machine learning model's performance. We have no way of knowing how well the model has performed because we don't really have the correct answers. Remember, when we calculated model performance measures, we usually use MSE for regression models and confusion matrix for the classification models. Now, the MSE is calculated by comparing the Y hat values to the actual Y values. You calculate the distance or the difference between the two, and then you add them up. When you have a confusion matrix, you have the labels, right? So the yeses and nos for the predictions and the actual. And so when the prediction and the actual are different, then you have a misclassification. You count the number of misclassifications, and that's how you calculate the error rate. Now, if there's no Y hat if there's no Y, then you don't really have Y hats, and you can't calculate MSE or the error rate of the confusion matrix. So in this particular case, when you only have X features and you don't really have a labeled Y response variable, then you are dealing with the question of unsupervised learning. So here's a visualization of supervised learning. So in this case, we have 2 X values, the advertisement amount, ad, and POP, P-O-P. These are 2 X's, and then you have a Y variable that's provided with the training data set that tells you the correct labels, the crosses and the dots, the zeros and the ones, or the negative ones and the positive ones. Using the X's and the Y variable, we can train the model. And once you have a prediction model, then you can use that to calculate your fitted Y hat values. And the Y hat values, when it's in a classification situation, we can further classify Y hats into 2 classes, 3 classes, and so on and so forth. The key is that when you have the Y and the Y hat, then you can compare the 2 columns, and you can use that to calculate how well your model has performed. And you can calculate this because you both have the Y hat and you have the Y, and you can measure the difference between the 2. Or you can count the number of misclassifications. Now, in the case of unsupervised learning, you will not have the Y column, which means you cannot calculate the Y hat, and or you cannot get classifications of Y hat values. And so the model performance measures that we've been using for supervised learning are simply unavailable to unsupervised learning. So in this particular case of unsupervised learning, when we only have the X features, then what we're trying to do is, instead of looking for the correct answer, trying to get the model to predict the correct answer, what we're trying to do is really just look for patterns in your X values and try to classify them, trying to find some sort of pattern so we can classify them in a meaningful way. There are two main methods of unsupervised learning that we're going to talk about. One is principal component analysis. The other one is clustering. In this lecture, we'll focus on principal component analysis. We first introduced principal component analysis in the dimension reduction chapter, where we had the challenge of having too many features, the X features. What we want to do is we want to consolidate the X features into a smaller set, and we call those principal components. We identify principal components using a process. It's called eigendecomposition, to find the direction in feature space along which data vary the most. And that direction will become our principal component. And the value of that principal component is a normalized linear combination of all the P features after we have centered them. Normalization means that we force the square coefficients to add up to 1. And centering means that we force the mean of the X values to be 0. We'll look at each of these in detail later. Principal component analysis, in a way, is like mixing a cocktail. You're taking all your X features and you're trying to find a way to blend them so that you can create a new sort of combination variable or value that is a little bit of X and a little bit of Y that maximally captures the variance within the data. The first principal component that we come up with always capture the most variance, and whatever that's left over can be then used to calculate the second principal component, and so on and so forth. So the first one is always more important, more useful than the second one, and so on. So the principal components come in an ordered way. How do we identify principal components? Like I said, this process is called eigendecomposition, which your book does not really go in detail. However, I'll try to explain it in a way that's accessible. So let's say that the principal component, if we call it Z, the Z-score, your book calls it Z, but usually in a lot of literature, you will see PCs, so PC1, PC2, PC3, Z is basically a principal component. Your book has the notation of Z. So I'll try to use both so that you don't get too confused. Okay. So we can formulate Z. The idea is to think about Z as a linear combination of all the X features. So you see X1, X2, all the way to XP are included in the first principal component. What we want to do is we're searching for these fees, Phi1, Phi2, all the way to Phi P, these what we call loadings or coefficients that will help us maximally capture the variation in the data. These loadings are normalized. Like we said, normalization is the process of making sure that the square terms of these loadings add up to 1. So once we've come up with the first principal component, we can use the leftover variation to figure out principal component 2 and 3 and so forth. You can have up to M number of principal components. M has to be less than or equal to P, or the number of X features. So the number of principal components can be no more than the number of P's you have. So here's an example from Chapter 6, Dimension Reduction. This is a data set where we only have 2 variables, population and add. So P equal 2, and therefore we can only have no more than 2 principal components. M has to be less than or equal to P, P equal 2, so we can have no more than 2 principal components. You can see that there are 100 dots on this in this data set, and they vary along both X variables. So population is X1, add is X2. We do not have Y values. So what we're trying to do is we're trying to find a direction that would maximally capture the variance in the data set. And you can see the data vary the most along the green line, and that becomes our first PC or Z1. The second line, which is purple, is perpendicular to the green line, and that will become our second PC. So because we construct these PCs, we can make sure that they're completely uncorrelated with each other. There's zero redundancy between the two. So we would draw the purple line, or the second principal component. When we draw it, it should always be perpendicular to the first one. Okay, so let's take a look at the data set. You can see the data vary along two axes, or the two X variables. The first one is called pop, and the second one is called add. The data vary, so some of them have high population, some of them have low population. They vary along the pop dimensions. You can see these are the ones with high population, and these are the ones that with lower populations. So you can see that, you can almost like see clusters of these two classes of data. The data also cluster along the ad dimension, so you can see those with higher ad spend, and then you also can see those with lower spend. So the question is, how can we find a principal component that will most capture the variation in this data set? So what we can do is we can, first of all, we need to center the data so that the mathematics depend on the mathematics of principal component analysis requires centering of the data set. So what we can do is we can calculate the means for add and the mean for pop, and that's where we find the center of the data set. And what we can do is we can shift the entire data set so that the center of this data set becomes zero, the zero origin. To do that, we simply have to take the value of each data point and subtract the mean of that dimension out of that value. So the values for pop can be subtracted by the mean of pop, okay? And we also subtract the mean of add from the actual add value. And you can see now the data set, the distribution remains the same, but the center is now zero. And what we can do now is to find a line, a principal component line that would fit through the origin that will maximally capture the variation of the data points. Now the question is, there are many, many different lines we can draw. Just like regression, you can have many, many different lines. Which line would be the best one? So this becomes an optimization problem. How do we find the best fitting line? We can define the best fitting line in terms of the projections. Okay, so these data values can project onto this line, and it will form a projection value. We can define best fitting line by in two ways. We can find a line that is closest to all the data values. So we can do that by minimizing the distance from the data point to the projected points. So you can see the blue lines. Those can be minimized. So we can call those deviations. It's very similar to the deviations that we talk about in regression. We can do that, or we can look at it as a way to maximize distance from the projected point to the origin. So the dotted yellow lines can be also measured as a distance, and instead of trying to minimize the blue lines, we can try to maximize the yellow dotted lines. So if we have 6 projections, the projections are the blue crosses, then we can measure the distance between these projections to the origin. So if we have 6 projections, we actually have 6 distances. And what we can do is we can add them up and try to maximize them. The idea is that if the data value is fixed, then the data distance to the origin is fixed. So the green dotted line is fixed, and we'll call that V, or the data vector or data value. Okay, so this one is, the green one is fixed. And the model is the yellow dotted line. We can move that, right? So we can rotate it up and down. So when we rotate it, the size of the deviation will actually vary. So D stands for deviation, is this blue line. And when the yellow line moves closer to the data point, D will decrease. When the yellow dotted line moves away from the data point, then D will become bigger. Now, when the projection line moves, the projection distance will actually go in the reverse direction of D. Okay, so P is the value of projection. When the deviation value goes down, P actually goes up. And when D goes up, P will go down. So the two of them, because V is a fixed value, P and D are negatively correlated with each other. So they will go in opposite directions. So if our idea is to find a line that will maximally captures all the dots, the model will need to minimize D. However, to minimize D, we are also at the same time trying to maximize P. So those are the same optimization objectives. Okay? The reason is V squared equal D squared plus P squared. And because V is fixed, D and P will just go in opposite directions of each other. So again, just to recap, there are two ways to define the best fitting line. We can try to minimize D, or we can try to maximize P. And in the principal component analysis mathematics, we're going to look at this as a maximization problem, trying to maximize P. Okay, so how do we do this? We can simply measure the size of these projections. So you can say P1, P2. These are just the distance of each of these projection points to the zero origin. And we can measure each one of these, and we can square them up, because some of them are positive, some of them are negative. We would add them up, and they become the sum of square distances. And we add these up, and we try to maximize the sum of square distances, and that becomes our principal component 1. So when we add these up, all these, I'm only showing P1 and P2, but there are actually 6 of them because we have 6 data points. This maximized sum of square distances is what we call the eigenvalue for PCA1, or we can call it Eigenvalue 1. It's a measure of the magnitude or the size of the first principal component. It's also what we'll call the variance explained by principal component 1. So one way to think about this is really the goal of principal component analysis is trying to maximally capture the variations, right? So thinking about that, sort of if we want to maximize the variation, the variation that is being captured along the principal component analysis, we want to make it as big as possible, and that's why we're trying to maximize the sum of squares of these p-values. And so when we add these up, because we already maximized these, and p can be considered the variation of each dot from the zero origin. So if we add all of these up for all the data values, then that's the total amount of variance that's being captured by the principal component. So hopefully these ideas make sense to you. And once we have the principal component, well, the p-values or the projections figured out, what we can do is we can normalize the singular vector. So the vector that is from the origin to the projected point, the blue cross, That is actually the vector that shows the direction of the principal components. What we can do is we can normalize the loadings by standardizing this vector to a singular vector that is the length of 1. Okay, because right now when we calculate the projections, we will have, once we have the direction of the principal components, we would have the length of, well, we'll have a slope of this line. That is this line over here is the model, and it has a slope, and you can decompose the slope into the x value and the y value, the rise. And you might have a y that is 1 over here. I actually have it over here. And then you will have an x value over here, and they will add up to this size. Okay, so the length of this projection is 1.838. What we can do is we can standardize it, and well, we can normalize it by dividing this value, making this length, forcing this length to be 1, and that is how we standardize it to be a singular vector with a length of 1. So in order to do that, basically we just have to shrink the size of the triangle proportionately, because we want this part to be 1, equal 1. What we do is we just divide it by the square of value of 1.838, and we do that to all the terms, and that's how we force this line, this length, to be 1. All these other numbers have been scaled down a little bit, and the scaled down value becomes the loadings. So these are what we call loadings of the first principal component. In order to get the loadings, all you have to do is build a principal component analysis model in R, and then you can use this notation $ rotation to access the list of loadings for the principal components. So once you have the loadings, this is your principal component 1, then this length becomes your theta 2 here, and this is your phi, not theta, phi 2 here, and this is the phi 1, and they will add up to the loadings. The squares of the loadings will add up to 1, and that is basically our eigenvector, or singular vector for PC1. It shows us the direction of PC1. So once we have the loadings, then we can put together our principal component 1. So once we have formulated this, then we'll be able to have our principal component 2. So once principal component 1 is set, then we look at whatever leftover variation we have in the data set. We can use that to construct our second component. The idea is that the second principal component has to be completely uncorrelated with the first one, and the fees have to be, in order to accomplish this goal, right, to make sure that Z1 and Z2 are completely uncorrelated, turn out that you need to make sure that the fees are orthogonal or perpendicular to each other. So once we have the principal component 1, then the second principal component has to be perpendicular to the first one, because in this particular case, we only have 2 features, pop and ed. There's no further optimization. We find the perpendicular line, and then the 2 of them will capture everything in the data set, as we can only have 2 principal components when you have 2 features. So the first one, okay, these are the loadings. And in order to, because the second line has to be perpendicular, there's only one possible way. So to figure out the second principal component loadings, we would just swap the numbers and make the second one negative. That's how we find a perpendicular line, and that's it. So these are the new loadings, 0.544 and the negative 0.839 are the new loadings for the second principal component. Your book uses an example where there are 50 different states. So you have 50 states. These are your n's. So you have 50 rows in the data set, and each state has 4 different x's. So you have x1, x2, x3, x4. These are the 4 variables that we measure for each of the states. We know how much the murder rate, the assault rate, the urban population level, and rape rate. Okay, so what we can do is we can run a principal component analysis and figure out the loadings for the first principal component and then the loadings for the second principal component. So these are your loadings. So your phi1, phi2, phi3, and phi4 for each of the principal components. Once we have these loadings, then we'll be able to construct an equation that will allow us to calculate the PC scores for each of the states. Okay, so the first PC score, the principal component score, is the loadings. So these are the loadings times the x values. So when you put these together, you can actually get a score for each of the states. So for example, if we're looking at Virginia, we can calculate a principal component 1 score for Virginia using this equation. And then using the fees from the second principal component, we can put together this equation that will allow us to compute the principal component score for the second principal component score, again for VA. So when you have 2 principal components, you can actually calculate 2 principal component scores for each of the records in your data set. And this is how we look at the data set using a visualization called biplot. You can easily plot this in R using the biplot command. Okay, so you will have calculated 2 PC scores, and then the biplot can just plot out the 2 PC scores. So the first principal component, each of the records, so there are 50 states, each one of them will have a PC score 1. Each of them also has a PC score 2. And using these 2 numbers, we can plot this graph to figure out where they are along these 2 principal components. As you can see, the loadings are being used to calculate these scores. And the loadings are actually visualized as these orange arrows on the graph. Okay. So here I'm going to illustrate how these loadings actually work. Right? So the first one is the arrow for rape, and that is the size of the loading right there. These are the loading vectors. Okay, the second one is assault, so that is 0.583 going in that direction, and then we have the murder 0.536. And then urban pop is only 0.278. So you can see that the murder, assault, and rape loadings are pretty similar to each other. They're all pretty strong. Urban pop, on the other hand, is a lot smaller. You can visualize this by looking at the size of the vectors. Okay, so the green vector for green urban populations is a lot smaller. So you can see that on the first principal component, it mostly captures the 3 serious crimes: murder, assault, and rape, and it cares less about urban population. So we can roughly say that principal component 1 captures how the rate of serious crimes in each of these states. Okay, once we have figured out principal component 1, the leftover variation can be captured by principal component 2, and you can see that principal component 2 again is a blend of all 4 X features: urban pop, rape, assault, and murder, but using a different recipe. So in this one, the urban pop gets a very high loading of 0.873. Okay, so you can see the size projected onto the second principal component axis is much bigger. On the other hand, if you look at the loadings for the serious crimes, murder, assault, and rape, they're much smaller. Okay, so which means that this principal component emphasizes more on urban population and less so on murders. Well, the serious crimes, because those have already been captured by the first principal component. So they still are in there, but they're not as important as urban population. So what we can say is that the second principal component is primarily a measure of how the extent of urbanization of each of the states. So we go from 4 X features, the raw features, rape, assault, murder, and urban pop, to just 2 major principal components. So we have kind of figure out how the variables cluster together. So in a way, this is really capturing the correlations among these variables, right? So rape, assault, murder, these serious crimes tend to go together, right? So there's some correlation among these, and they're less correlated with urban population. So basically, you're identifying 2 sets of variables that are relatively independent of each other. So the insight from principal component analysis is really the clustering of these features, right? So we say there are 3 crime-related features that are correlated with each other, clustered together. Urban pop is less correlated with the other 3, so that is a relatively independent or orthogonal dimension. So basically, there are 2 sort of big factors that we should consider when we look at these states. So let's look at individual specific examples, right? So California, when you look at California on the graph over here, you can see that it's high on both principal components, both high on crime and urbanization. So it's in the upper right corner of the graph. Vermont over here, on the other hand, is pretty low on both principal components, very low on crime and also very low on urbanization. So these 2 dimensions will be able to separate. So California, you can basically argue that California and Vermont differ from each other significantly. You can segment these 2 states very well just by looking at these 2 big vectors. Virginia, on the other hand, it's right in the middle. That means that it has not 0 crime rate. It's just this 0. It's a centered value. This is centered. So that's just the mean. So 0 means this is centered around the mean. So 0 just means that Virginia has an average, right? So it's an average rate of crime and average rate of urbanization. It's right in the middle. All right, so those are the main concepts of principal component analysis. These are some of the very useful commands that you can use in running principal component analysis in R. We use the command prcomp. Okay. In the library stats, you don't have to load anything. It's a very basic, very standard command that's available it's been around for a long time. And you can use that to run your model. And once you have your PCA model, then you can get a summary report using the summary command. And then there are all sorts of, the model has all sorts of properties that you can access to review the model. So for example, you can get center, that's a list of raw variable means. You can also get the raw X variables standard deviations by using $scale. You can get the loadings by calling $rotation. You can also get the scores, the principal component scores of each of the data values using $X. So it's very important to know that these are not the raw X values. These are the calculated PC scores. You can also get the standard deviation of the PCs by calling SDEF. And then once you square the standard deviation of the PCs, the principal components, then you can get the variance explained, which for each of the PCs, which is basically the eigenvalue that we've been talking about. So that's how you will calculate that, the variance in R. You can also plot very easily using the biplot command to plot the first two principal components. So that's all for the first part of the principal component lectures. Hopefully I'll see you soon in the second lecture.